Assalamualaikum and selamat sejahtera. Today, I will explain about rectifiers. In power electronics, rectifiers are used to convert AC power to DC power. Rectifiers can be classified based on three criteria. First, it is based on the AC sources connected to the rectifiers. Second, it is based on the power switches used in constructing the rectifiers. Lastly, we can classify the rectifiers based on their operation. If the rectifiers are only capable to rectify the positive half cycle of the AC supply voltage waveform, then we call the rectifiers as half-wave rectifiers. On the other hand, if the rectifiers are capable to rectify both positive and negative half cycles of the AC supply voltage waveform, then we call the rectifiers as full wave rectifiers. Figure 1 and Figure 2 show the circuit topology of single-phase uncontrolled half-wave and full-wave rectifiers respectively. Based on the figures, we can see that the half-wave and full-wave rectifiers are using a different number of diodes. This situation can be explained using a single-phase AC supply voltage waveform. Figure 3 shows a complete cycle of the AC supply voltage waveform. Based on the figure, we can see that the waveform consists of one positive half cycle plus one negative half cycle. Since the half-wave rectifier is designed to rectify only the positive half cycle of the AC supply voltage waveform, therefore, we only need a single diode to connect the AC source to the DC load. On the other hand, the full-wave rectifier is designed to rectify both positive and negative half cycle of the AC supply voltage waveform. Because of that, we need at least two diodes to construct the full-wave rectifier circuit. However, in order to perform full-wave rectification, the rectifier must be connected to the AC supply through a single-phase center-tap transformer. The center-tap transformer will split the input supply into two AC sources. Then the full-wave rectification can be conducted. This topology is known as a single-phase uncontrolled full-wave rectifier with center-tap transformer. If you want to remove the center-tap transformer, then you can remove it by adding another two diodes. Therefore, in total, we have 4 diodes. And this circuit topology is called bridge rectifier. And as similar as the half-wave rectifier, all these diodes will connect the AC sources to the DC loads. As mentioned before, a rectifier converts AC power to DC power by controlling the current flow using power switches. In the context of the uncontrolled rectifiers, we need to focus on the operating conditions of the diodes. However, we must assume all the diodes are ideal. As the direction of current flow depends on the polarity of a voltage source, it's better to explain the principal operation of the rectifiers based on the waveform of a single-phase AC supply voltage. During the positive half cycle, diode D in the half-wave rectifier is in forward bias. Hence, it creates a closed-loop circuit to conduct current from the source to the load. Meanwhile, in the bridge rectifier, diode D1 and D2 are in forward bias. Thus, current can flow from the source to the load. Here we can see the bridge rectifier requires a pair of diodes to conduct the current. On the other hand, in the split supply rectifier, only diode D1 is in forward bias. Hence, current will flow from the source to the load. Next, when the half cycle of the AC supply voltage waveform is negative, diode D in the half-wave rectifier is in reverse bias. As a result, it creates an open-loop circuit and therefore current cannot flow to the load anymore. Nevertheless, in the full-wave rectifiers, current is still flowing to the load. It is because in the bridge rectifier, diode D3 and D4 are in forward bias, while in the split supply rectifier, diode D2 is in forward bias.